Assalamualaikum warahmatullahi wabarakatuh and a very good day to our lecturer, Dr. Farah Zayana binti Ahmad Zulkifli and our fellow friends. Today we're going to explain in details the high performance liquid chromatography or HPLC experiments. The content of this video included the introduction, objectives of this experiment, methodology, results and discussion, and lastly the conclusion that conclude these experiments. So let's start. We have 6 group members that conduct this experiment together. The first one is me, Nur Kamarina binti Muhammad Alimi, with ID number 2022619988. The next one is Nur Farahuda binti Mansur with ID number 2022699756. The next one is Siti Soleha binti Muhammad Sata with ID number 2022X43838. The next one is Siti Nurfatina Juan binti Suhaimi with ID number 2022881364. The next one is Nurliana binti Rudi with ID number 2022869736. And the last one is Intan Farisha binti Shariman with ID number 2022892882. So this is the introduction for this experiment. High-performance liquid chromatography, or known as HPLC, is a popular analytical method of chemistry and biochemistry for the separation, identification, and quantification of constituents in complicated mixtures. It is a vital instrument in sectors including biotechnology, food and beverages, pharmaceuticals, and environmental study because of its high resolution, sensitivity, and adaptability. The distribution of the analyte sample between a stationary phase, column packing material, and a mobile phase, eluent, forms the basis of the HPLC separation principle. The molecules are slowed down when they travel through the stationary phase, depending on the analyte's chemical structure. A sample's on-column duration is determined by the particular intermolecular interactions that occur between its molecules and the packing material. As a result, distinct components of a sample elute at various times and the ingredients in the samples are separated. The main goals of these experiments are to analyze a mixture of substances, optimize chromatographic settings, and comprehend the basic ideas of HPLC, determining the retention times, computing the resolution between peaks, and assessing the system's effectiveness with theoretical plates are important goals. The significance of method development and its applicability in actual sample analysis is highlighted by this practical experience. By the end of these experiments, students will have a solid basis for future analytical chemistry applications, having gained hands-on experience with HPLC instrumentations, sample preparation methods, and data interpretations.
Okay, next is the objective. First is to determine the retention time of a standard solution. Secondly is to identify the caffeine peak in a soft drink sample. Last but not least is to determine the amount of caffeine in a soft drink sample using the response factor method.
Hi, my name is Novarohuda binti Mansur and I will explain about the methodology of the high-performance liquid chromatography HPLC. HPLC consists of 6 components which are solver reservoir, pump, injector, HPLC column, detector, and data acquisition. First, we have the solver reservoir, or known as mobile phase reservoir filtering. Mobile phase are contained in the glass reservoir filter to connect the pump inlets into burst gas used to remove gas. A glass reservoir holds the mobile stage ingredient. In HPLC, the flexible stage or dissolvable is often a mixture of polar and non-polar liquid segment which specific physician change depending on the specimen arrangement. Next, the pump system was developed as the result of development of HPLC. The pump is located in the upper streams of liquid chromatographic column and pump eluents into the system from the solver reservoir. It is to deliver the mobile phase at constant flow rate. Next, we have injector. Injector is responsible for introducing the sample into the mobile phase, which allowing different methods such as string injection, sampling loop, and auto-sampler. It handles liquid sample volume ranging from 0.1 ml to 100 ml. Next, we have HPLC column. HPLC column is to separate each compound contained in the sample. There are two types of column, which are guard column and analytical column. The choice of column depends on the types of analysis being performed. Next, we have detector. The detector is a device that is used to continuously monitor the compositions and content change of the influence separated by the chromatographic column. It is one of the three key components in an HPLC system. The detector requires high sensitivity, low noise, that is insensitive to external changes such as temperature and flow, wide linear range, good repeatability, and wide application range. As we have the data acquisitions, then we'll process the signal received from the detector and generate chromatogram. This system can collect, store, display, print, and process the test data so that sample separation, preparation, or identifications can be carried out correctly.
Next, I will talk about result and calculations. So as you guys can see, we have the chromatography for caffeine. So first of all, we need to calculate the RF, which is response factor of the caffeine standard. To calculate the RF, we need to divide the area peak area caffeine standard with concentration of caffeine standard. So as you guys can see, the value for peak area caffeine standard is equal to 6249.40 divided by 100, which is concentration of caffeine standard, and we will get 62.495. Next, after we got the value for RF, we can calculate the concentration of caffeine in the Coke drink. The formula to calculate the concentration of caffeine is peak area caffeine divided by response factor RF, which is we have calculated before. So the value for peak area caffeine is equal to 7001.12 divided by RF that we got, which is 62.495. On the chromatography, we can see that the caffeine peak in Coke is the tallest peak, which is the peak area for the tallest peak is equal to 7001.12. Lastly, we got the concentration of caffeine for Coke is equal to 112.03 ppm. Lastly, we can calculate the concentration of caffeine in the Vita ring. It's same with Coke drink, which is the peak area caffeine divided by response factor RF that we calculate earlier. The caffeine peak in the chromatography of Vita at the fourth peak, which is the peak area, is equal to 11151.1 divided by RF, which is 62.495. Therefore, the concentration of caffeine in Levitra drink is equal to 178.43 ppm.
My name is Siti Soleha binti Muhammad Satar. For this part, I will present about discussion. In this topic, there are three chromatograms which are caffeine, Coke, and Levitra. From the chromatograms, the rotation time of caffeine can be determined, which is at 2.482 minutes. This means it takes 2.482 minutes to travel from the injection to detector through the column. Also, the rotation time of caffeine peak in Coke and Levitra can be identified from the chromatograms. For Coke, the rotation time of caffeine peak is 2.481 minutes. This shows Coke having the highest peak. However, for Levitra, the rotation time of caffeine peak is 2.479 minutes. From the calculation, the concentration of caffeine in each drink are obtained. Coke has 112.03 ppm, while Levitra has 178.43 ppm. This shows that Levitra has the higher caffeine content than Coke.
Hi, my name is Siti Novatina Najwa, and for the last part of our video, I will talk about the conclusion. From this video, the main objectives were successfully achieved. The retention time of each standard solution was determined as follows: caffeine at 2.482 minutes, Coke at 2.481 minutes, and Levitra is at 2.479 minutes. The caffeine peaks in the soft drinks sample were identified, with Coke peaking at 1,465.597 MAU and Levita at 2,389.65 MAU. The amount of caffeine in Coke is 112.03 ppm, approximately to 57.36% of caffeine. While in Levita, it is 178.43 ppm, approximately to 17.70% of caffeine.